Hello. Let's pause this. Okay, hopefully you can see me now. I mean, I know you can. Okay, this is chapter 6. It's the ocean floor and the coast. You guys have your study guide for it. You already have your notes done, or should have your notes done. One second. Okay, so the ocean floor and the coast. Your vocab words: continental drift, continental or convergent boundary, divergent boundary, continental shelf. I'm reading across. Plate tectonics, subduction, mid-ocean ridge, continental slope, lithosphere, and then that is as Latin root words to it. Trench, transform boundary, continental rise, asthenosphere, and asthenos means plasticky. Lithos means plate or like land. Volcano, abyssal plain, isostasy. Iso has that connotation that it's equal. Like isotonic, like when a cell is in a solution that has the same amount of dissolved particles, you would say it's in an isotonic solution. Isosceles triangle is a triangle with equal sides. So iso is going to be equal, and that's going to be like that balancing, that similar to buoyancy. Mantle, earthquake, hydrothermal vent, beach renourishment. Convection current, tsunami, continental margin, morphology, erosion, deposition, estuary, delta, zonation, desiccation, in fauna, sedimentation, littoral zone. Okay, so how marine science and being able to discover the ocean changed at the Second World War. We had developed really advanced technology so that we can detect any underwater submarines, and this is what we use sonar for. So it stands for sound, navigation, and ranging. So it allows us to see what the ocean floor looks like based off sound waves and based off the rate at which they reflect back. You can kind of get a picture of it. And then it was followed by scuba. And scuba is self-contained underwater breathing apparatus. And that's when you're breathing with your oxygen tank. Okay, how plate tectonics came to be. We had a scientist and I guess the explorer, Alfred Wegener, but it is like, it's not Wegener. That would be American. He is German, Alfred Wegener. There were three things that really allowed him to think like, what's going on here? Maybe these places were closer together than they originally are. Talking about like continents. He's talking about like continental comparisons. So, and that led to the theory of plate tectonics. So he noticed that there's similar fossils of plants and animals on continents that are separated from each other. For example, Brazil and in Africa, right? They're divided by a huge ocean, but yet they have the same fossils and of plants and animals. So if they weren't once together, your option would be that perhaps those animals flew or swam or got stuck on some sort of oceanic vessel that did make its way across the ocean. A seed flew across the ocean, landed in one of those, would have landed in Brazil and then started growing there, would have originated in Africa. The second one is that he found similar geological structures. So again, that South Africa and Brazil situation, there's similar rock formations that in age and in composition, the rocks that they're made of are very similar. And then if you would have cut it and then split them apart, what would be on each side of the ocean would have been same rocks. Olive's screaming for me. Hopefully you can't hear her. The Appalachian Mountains in Virginia, West Virginia, Kentucky, also in North Carolina, those match those of the West Highlands that are in Scotland. So again, just saying that like they were once together. The shoreline and the shape of the continents seem to fit together like a jigsaw puzzle. And I know that idea was really reinforced in 7th grade science in Florida. So this led to the theory of continental drift, or that continents are floating on top of the Earth somehow. And this was able to support the idea that there are continents that are moving constantly on Earth's surface. Based on their rate of movement right now, it's very slow, right? Based on their rate of movement. So we think like the Atlantic is spreading apart like 1 to 3 centimeters a year. Well, if we took the entire depth and the entire length, entire width of the Atlantic Ocean, and we know that it's moving at a rate of 3 centimeters a year, then technically we could backtrack it. Okay, how many total centimeters is the Atlantic Ocean? And if it's moving at 3 centimeters a year, how long ago was it that those continents were actually together? And so that's where they came up with the number about 300 million years ago. MYA is million years ago. And they called this supercontinent, all the continents together, Pangea. Pan means entire, and Gea is Earth. It was not well perceived by the public at all, to even think that these things were moving. They were once together. Everybody likes to think that time started with them. And that's not necessarily the case. Something else that it's not on here, but I learned last year is Pangea is like the 7th or the 8th supercontinent. There's a lot of other research and data. What's to say that Pangea was the first one? Why would it have even been the first one? It didn't even have to be. Anyways. Okay, so the theory of plate tectonics. This was Alfred Wegener's idea that, are these continents moving? And then really the idea of plate tectonics then birthed from this. We think the continents are moving. We think they were once connected. But what is the mechanism that's actually moving them? Okay, so this is how the continents are moving. Again, continental drift is the idea that they are moving, but the public was like, cool, what a crazy idea. You didn't tell us how. You didn't give us a mechanism, so we don't believe you. So this was the mechanism of how the plates are moving, and this is plate tectonics. Okay, so it's the process where large sections or plates, we call that the lithosphere, are constantly moving over this fluid mantle. At the very top of the mantle, we have the asthenosphere. Astheno means plasticky, so it's like this. It's like this in between solid and liquid. It's such a dense and thick liquid that it is a little bit solid-like. So when they made this weird of the word asthenosphere, they were really comparing it to something that may have been plasticky that it's able to float on. I've seen or read whatever examples that we could compare this to cookies floating on top of milk or whatever. Except eventually those things are going to absorb and sink, and that's not the case for this. Excuse me. So it's led to the theory of plate tectonics, so that these large pieces are floating over Earth's crust, over this fluid mantle. The reason for the fluid mantle, I don't know if you guys can see these updates. Okay, hopefully you can. Get out of here. Oh my gosh. Sorry. How do I close it out? Get out of here. Okay, I'm sorry. There's a million updates that just came on. Man, they're still happening. This constant movement is going to be what is the culprit for our earthquakes, for our trenches. They are not the main cause of landslides, but they can influence landslides. Volcanoes, mountain chains, underwater volcanoes, the spreading of our oceans, the opening up of rift valleys in Africa, the continuation of the Himalayas growing, the Mauna Loa, where in Hawaii, the island of Mauna Loa, yeah, whatever. This summer they've constantly had this active earthquake, and over this summer it was too active for people to actually see it. But this is all because of plate tectonics, which are awesome. It's my favorite part of the rock cycle. Just to see this huge planet-size recycling, this rejuvenation of the earth, that the old gets taken back in and refreshed and then brought back out. Hopefully it's really symbolic of our life as well. Our nature does this. Our bodies do this every day on a cellular level. And our planet's doing this, on a global, universal time scale. It's pretty amazing. Okay, so then our lithosphere is the outermost layer of many plates, and this is what is moving in plate tectonics. Each of these plates can float independently on this nearly liquid asthenosphere. And these are on the asthenosphere is the uppermost part of the mantle. Now, I showed in class kind of how convection currents work. It is this area right here that is doing this convection current. Let me see if I can get something to draw here. I sure can. Okay, get some red. Okay, so right here in our core, okay, we have an inner core, an outer core. Now the inner core is solid. Even though it's the hottest part of the earth, the inner core is solid because of all of this pressure pushing down on it. Temperature and pressure can change you from being in a liquid, solid, or a gaseous state. So yes, it's very hot, which would make you assume that it could go into a vapor, or at the very least, it's going to be a liquid. But yes, the temperature is really high, but the pressure is even greater. So that pressurizes that to be a solid. The outer core is liquid. And then our mantle is also liquid. And then the asthenosphere, it's like this weird liquid kind of turning really thick, almost like a solid, but not yet solid. It still moves. It still flows. Okay, so in the mantle is where all of our lava is. Okay, and down here it's really hot. And think of like a lava lamp. Think of a lava lamp, right? Here's our lava lamp. Okay, here is our light source. Sorry, I'm drawing it. It's a light bulb. Okay. It's in this bottom portion. And when the lava gets at the bottom, it gets pretty thinned out and heated, and then it moves back to the top. Not the lava, but in the lava lamp. At the top, it's not by that light, so it gets cooled down, and cold things increase in density, and then they sink. And then it gets warm again by the light, gets a little bit more fluid, moves to the top. Same thing's happening in our asthenosphere. I would like to change the thickness of this, and I don't know if I can. Maybe I can. I don't think I can. So again, the lava in here is going to get pretty hot, and it's going to make it become less dense and rise. Once it's at the top of the asthenosphere, it's going to be away from a heating element, and it's going to cool down. So hot, right? Still really hot, but it's going to cool down in comparison to what it was and increase its density and then sink again. You're going to get closer to the bottom, less density, increase. And then this is happening over and over and over the entire planet, over and over and over. And this is allowing that constant floating and pushing and moving underneath. This is what causes plates to get pushed together, and build. And then one has to move, and that's going to cause an earthquake, volcanoes. Volcanoes are just building up over time, and then just that breaking, that pressure builds too much and it explodes. Come on. Oh, gosh. Why does it stay on this whole thing? What a flaw. What a flaw. Oh, I'm going to pause it and get rid of this. Deleted it. Okay, I'm not going to go through these videos right now because I've already seen them. But if I were teaching this in class and lecturing in class, I would make you watch these videos and take notes on them. So don't skip it because I'm not forcing you to watch them in class. I know that these are going to be influential in helping you kind of identify what's going on in the earth, why we're getting bigger oceans, what we project the earth to look like 100 million years from now. Where did water come from? I do expect you to watch these, and I'm not gonna, pause it and do it right now because I've already done it. I expect you to watch these, so take some time to watch them. I only put up things that I think are worth your time. Okay. So what is helping support the theory of plate tectonics? You do need to know what these supports are. Typically, the question asks for 3. And you're going to have a lot to talk about. But typically, the question asks for 3. You guys saw it in the assignment you did last Monday. I'm trying to see your third one. Okay. Okay. The next two pieces of evidence to support plate tectonics are really going to be what happened after the invention of sonar in scuba, but mainly sonar. So the two that we've already talked about that are not going to be following this next segment is going to be them fitting together, continents fitting together like a jigsaw, and having similar fossils found on continents that are apart from each other. There also is a link right here. If you click plate tectonics, click that link. Hey, yeah, watch this video, click this link, watch the video about plate tectonics. It again talks about the lithosphere, your ionosphere and crust being together. If you drained the oceans and you took the vegetation off, what would our like Earth look like? Because there are cracks on the outside of the Earth, kind of like you think about cracking an eggshell. There are cracks on the outside of the Earth, and that is, sometimes the plate will carry land, sometimes it carries ocean, or sometimes it has both on there. So what sonar has allowed us to do then was in the later 70s, Marie Tharp, and a geologist, and she was a geologist, she was also an ocean cartographer, which means that she makes carts. No, I mean, she makes maps, not carts. And she had a partner, Bruce Heason. They worked together for about 20 years. They were on a boat or a ship, and they used sonar to map the world and where the plates were, map the oceans, and it allowed us to be like, yeah, maybe Alfred Wegener wasn't such an idiot. Like this, there might be something to this. So if we're looking closely, we can see where we have right here. We know this is already a divergent boundary. We're splitting apart. This is the mid-ocean ridge. What makes a ridge is that it's the volcanic magma coming out, and it solidifies into this basaltic rock. Basaltic rock does have magnetite in it, so it does carry magnetic polarity. It does have a magnetic response. Over here, we have subduction happening. Not spreading, we have subduction. We also have subduction happening right here. We have very, very, very deep trenches right here. I'm not exactly sure, but I believe the Marianas Trench is right in this area, and that's the deepest part of the world. But super deep trenches here, followed by very high rise or like a high relief area that will raise the seabed. It is this Pacific area, that is slipping under this plate right here. This big plate right here. Our Pacific plate is slipping under it. I believe this is called the Eurasian plate. This is also part of Eurasian plate. All right. So they don't all have to move the same direction. Depending on what other plate boundary they're touching, sometimes they're moving like a transform boundary, parallel. Sometimes if one's moving transform, it might be hitting another plate and hitting it convergently, causing subduction or causing volcanoes or earthquake. Nope, mountains. It depends. Sometimes they're spreading apart from each other, moving apart. This area is moving apart right here, moving this direction, causing it to close up on itself towards the Pacific. And then we have magnetic polarity reversal. So this is going to be the different polar changes in your basaltic crust. Basaltic rock is formed when magma solidifies. Basaltic rock is formed when magma solidifies. Basaltic rock is formed when magma solidifies. Okay, when it comes out of a volcano, it's also called an igneous rock. Okay, basaltic rocks, I want to say are oceanic, specifically oceanic. It's, yeah, okay. So this is, again, it measures the magnetism of the ocean floor using magnometers. Sailors also noticed this when their compasses were changing, and they're like, what, why is it changing? Why is it, my north is not my true north anymore? And but this is because as this basaltic rock comes out from our divergent boundary, and we can see this in the Atlantic mid-ocean ridge on this guy right here, all the way down. As we move towards the left, we move towards the right, we can see this consistent magnetic polarity reversal. Again, basaltic rocks line the ocean floor. They have magnetite in it, so they are magnetic. They can reveal that the Earth's crust is laid out in alternating positive poles, negative poles, positive poles, negative poles, positive poles, negative poles as it moves out. Okie doke. The evidence will show that the striping pattern started to begin when the mid-ocean ridge was really weakest and magma was able to push through. And it's this pushing through of magma in this area here that's very vulnerable that's making this continually spread, continually spread, continually spread. If this is continually happening, there's really no way of this to solidify and like stop. It's going to be a constant movement. Okay, so again, basaltic rocks are found in the seabed. An example of a basaltic rock is an igneous rock. There you go. Igneous rocks are created when magma cools and hardens. When igneous rocks, within igneous rocks, is naturally occurring magnetite. When magma hardens, the magnetite will align itself with the polarity of the Earth's crust, and it will become solidified that way. It takes about 250,000 years for reversal to occur, and I'm not entirely sure, but I believe it has a lot to do with the way the Earth is tilting. Excuse me. But that's not a consistent timeline because it's been found that within that 250,000 year period, we have had reversal twice. And so as our divergent boundaries where the mid-ocean ridge is, magma from the mantle is coming out and hardening into igneous rock. Excuse me. We can, I spelled parallel wrong. How exciting. Sorry, I have a million updates on this computer. As those polarities are changing, as they're radiating out from that divergent boundary, that splitting boundary, and that magma has become solidified, again, inside that basaltic rock, inside of that magma, there is magnetite. It will solidify and orient itself based on the polarity of Earth. That's probably hard for us to understand, and I can't agree more. Completely agree. This is one of those things that I read out loud, and I'm like, okay, I believe that can happen. You know, I'm sure you have evidence for it. Great, 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 great. We've just never seen this happen. We've never seen I've never seen like an opposite pole attraction where my north is not my north anymore. My north is my south. Neither have you, because we have not lived for 250,000 years. So. Okay, so plate boundaries. There's 3 different plate boundaries. Again, this is a review from 7th grade if you attended 7th grade in Florida, or at least in Brevard County. So lithos is plate and asthenos is weak. I know asthenos, when I was doing research on that word, it also means plastic-like. But in order for the lithosphere to move, the asthenosphere must be moving as well. And it does move. And it moves because of those convection currents in the mantle, and it's pushing it all. The lithosphere has the Earth's crust, and it also has the asthenosphere on it. Okay, so the lithosphere is the Earth's crust and that plasticky asthenosphere layer. That entire part is called the lithosphere. And we have mantle, outer core, inner core. Again, so back to your convection currents, and I drew this out for you a few slides ago. It was like the lava lamp. So with your convection currents, they're moving based on density. Air does this as well. The ocean does this as well. Your drinks do this constantly. Your warmer part of your drink, or like if ice starts to melt, what's less dense, then like your soda is going to be just plain water, and that water is going to float to the top. So you see this everywhere, and you know it's just science is so cool that we can see things that happen. You know, like nature is so consistent and physics is so consistent. We can see things that happen on such a small scale. You know, like density is also what moves things around in our body, and that concentration gradient idea. And same thing here. You know, something that is way more dense is going to sink because a higher density is pushing it out of the way. Like, it's just, I love that it's consistent, that we can see things happening on a tiny scale in our coffee cup, and we can also have things happening on a huge planet scale. What happens in our coffee cup and what happens in our soda is the same thing, and in our bath is the same thing that's happening in the inside of our Earth that is moving and making all of our geological processes. So if you don't like plate tectonics, either you didn't watch the cool video slide, and you should give that to yourself. You should learn everything you can, or you just don't understand it. Like I say about photosynthesis, if you don't love photosynthesis, you don't understand it. Okay, so I've mentioned convection currents in other slides. We have convection ovens, same thing. The hot air is going to rise, causing the colder air to sink. It gets warmer by the heating element, and then that cold air gets hot and it will rise, and then it cools down and starts to sink. And so convection ovens work the same way. So again, it's the movement of fluid or air based on density differences, and this is caused by different temperatures. Temperature can cause a density difference. Pressure can cause a density difference. As the magma moves, the temperature changes, and this will change its density. So when it's hot, it's less dense. When it's cold, it's more dense. Convection will occur, or the movement of things that are hot and sinking of things that are cold, because the density changes. As magma heats up, the molecules spread out, becomes less dense. The cooler the magma rises above. Now, this is also how we can move oceanic currents around. However, many times they are stuck not moving because of your thermocline. It's such a drastic difference. You have solids that are sinking, increasing the density at the bottom, and then you have a lot of heating at the surface and no heating at the bottom. It's hard for water to even do convection from the surface to below the thermocline, because of the thermocline. That temperature difference also causes a density difference, and we call that the pycnocline. In Chapter 7, we'll talk about the halocline, which is a salinity difference. Okay. Magma nears the asthenosphere, it cools and then begins to sink, and then that whole movement is able to move your lithospheric plates or your crust above it. The lithosphere is very heavy, and convection is very slow. So these plates are only moving 2 to 5 centimeters a year. And these small movements, we're pushing extreme solids by each other, extreme solids. So there's just the global scale of these huge plates moving is crazy. We can see what happens in a car crash, but this is like a global planet crash. Okay, we can have a divergent plate boundary. And to diverge means to go apart. To verge off something is to go apart, and die is to. So diverge. The opposite of diverge, I'm going to go to the bottom right here, is to converge, like to come together. Converge, coming together. And then we have a transform plate boundary. It's also called a conservative plate boundary, and that's where the plates are moving side by side to each other. So divergent moves apart. Transform, they slip against each other. And they're rock, so it's very jagged. It's a very hard slip. If you ever accidentally scraped your car against a pole at a gas station or in a drive-through, not speaking from experience, then it is a little bit rough. It's not very smooth. And again, this is on a global planet scale. And then we have our convergent plate boundaries. If it's land and land coming together with equal densities, they're just going to push each other up and create beautiful montañas, which is mountains. If it's land and ocean, my ocean, we'll do this one as the ocean, is a little bit more dense, just a little bit. So that means it's going to be heavier and it's going to sink underneath. That is called subduction. There you will get a volcano. And right where my knuckles are hitting my fingers, right here, that is going to create a trench. And it's the deepest part in the ocean. Okay, and it can cause a volcano. This rock, my fist rubbing against the palm of my hand, we can make heat doing this. But when we're talking about very thick, very heavy, dense, planet-sized rock moving down past each other, where my knuckles are, that oceanic plate that's more dense will start to melt, literally start to melt. You could melt your skin and your hands and your bone, but you just can't move your hands fast enough. But you totally could. It's going to start to melt, and that liquid is less dense compared to the solid that's going underneath. So that liquid's going to float up and up and up and up. And as it's going down, it's going to push and push and push and push, and then we'll have a volcano come through. Ha! Here I am. Okay, so Mount Everest is a result of convergent boundaries, and it's still moving. It is still moving. The Himalayas are still getting bigger. Here's our Himalayas right here. Millions of years ago, 71 million years ago about, India was a separate landmass, and it's floating. The only reason we have land, I want us to watch a video about how did Earth form. I showed it to my environmental class, but it is also very pertinent to this chapter, but it is about like an hour. So it would take a couple of class periods to do this. But it's all started out as water. It's not like, boom, the planet came about and all of a sudden it has all these layers and it has this convection situation. And we're like, boom, here's some land, here's some water, go team. It's not how it started. Everything was water. And then once we had these, violent reactions within our crust, and the underneath of our Earth is starting to break through these, porous or vulnerable areas or thin pieces in the crust, we started to create land whenever it solidified. Anyway, so an example of convergent boundary, here we go, and it's still getting bigger because it is still moving. And here's Mount Everest, our tallest mountain. It can get taller. And I'm going to move myself out of the way. Moving myself. No, I'm not. Wait, yes, I am. Okay. Here's our Himalayas. So we can see what's causing that. Fun. Okay. Oop. Yep, you can see what's causing that. So we have the Indo-Australian plate pushing towards the Eurasian plate also is now in the way. It looks like there is subduction, but I mean, it has to go somewhere. And essentially, it's just lifting the lithosphere above it. Lifting. Like if in a car crash, if those cars didn't like diverge and move away from each other, they would just be building on each other. Imagine two hit each other and they didn't have wheels. They didn't bounce apart. Instead, they hit each other and they're just building. And then more cars are in that crash and they add to it. And then the crash never stops and it'll just keep growing. Okay, I'll move myself over again. Convergent boundaries and their features. So what you see at convergent boundaries, hopefully you're kind of taking note that what we've done so far in our bell work, that you need to know what these features are and how these plates are moving. Based on the features, you should be able to identify what kind of oceanic boundary it is, or I'm sorry, what kind of plate boundary it is, not oceanic. So convergent is two plates coming together, converging. So it's also called a destructive boundary because it's destroying land. So not divergent, destructive. Convergent, you're coming together and they're destroying each other. At these boundaries, we can have subduction zones. Again, we're destroying land. It's going underneath this lithospheric plate. I would love to draw arrows, but I know it's going to stay. This lithospheric plate is moving underneath this continental crust. Again, the continental crust is less dense than the oceanic crust. The continental crust is way more thick. How do we know that? Well, our land is above sea level, isn't it? For the most part, unless you live in Florida. We're only like 5 feet above sea level. But like my hometown in Ohio is almost 300 feet above sea level. I don't feel like I'm that high in elevation by any means, but it is. So continental crust is higher than the ocean. And that also will go to that idea of like isostasy, that our land can float. It is less dense. It is more thick. That doesn't matter. It is thick. I mean, it has mountains on it. That should be a huge identifier that it's thick, but it's not as heavy. It's not as dense. That's like saying, what if I had, a piece of iron only this big, but I had a feather that was as long as my couch. What's going to be heavier? Yeah, the feather's really long, but it's not as dense. There's not as many particles per area. Anyway, so this is what's happening here. Our oceanic crust is converging with our continental crust, but because oceanic is more dense, it is sinking. I just got an alert from my fantasy football. Mitch Trubisky's out. Not a big deal. I don't start him. But he is from Mentor, Ohio, which is my hometown. Then he played at UNC, and then he got drafted as the second pick in his draft year, and he plays for the Bears. So, Ohio. Anyhow, subduction zone. Oceanic crust is subducting underneath the continental crust. What are we going to see there? And again, this is because the oceanic crust is more dense. Know that. This is called a destructive zone. It's destroying the land. This is what I was talking about. Is they're rubbing together. It's so hot. This plate is moving underneath, if I'm mimicking what you guys are seeing on the screen. And this movement right here is melting, melting, melting. Well, again, that liquid things are less dense. Less dense things want to rise. So as my heavier mass, land mass, that solid is moving down further, that liquid's like, wait, and then it'll shoot through and it'll start to make a volcano. Now, if this is like an area right here where the magma can come through, why would it stop there? It's going to keep growing and growing and growing. Unless it moves over that hotspot area, unless it moves over that area where your volcano is popping through. The plates aren't as active there, but it takes a long time for them to move away from that area. Okay, what are we going to see at subduction zones? Not convergence, but subduction zones. We're going to see trenches, the deepest part in the ocean. It's the Marianas Trench. We're going to see volcanoes, because this melting lava is moving up because it is less dense and it's popping through the crust. Now, with that being said, this is super hot. This is super, 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 super hot. Doesn't happen right away. It does take time for this to start melting. But as this is melting, it's moving up, it's melting rock around it. It's melting a lot of rock around it because it is so hot. And to me, it just blows my mind, the idea of melting rock. Like, the friction and the pressure has to be so high in order for you to melt that kind of solid. The solid that creates our foundation of Earth is being melted. And then out comes these volcanoes. All right. You also see tsunamis, and you can also have earthquakes. Just the slipping, it could be constant, or it could be pretty infrequent. You know, you might have this plate just trying to move down. You know, thousands of years have gone by. Maybe not even thousands, maybe just a couple hundred have gone by, and it's pushing, and then all that pressure builds, and finally the pressure is too much and something gives, sinks a little bit further. That moves the whole ocean basin that it's in. And that moves the whole Earth. That huge movement radiates in that whole Earth. This can cause huge tsunamis to just, you know, it's kind of like moving your bathwater. It's going to just slosh back and forth, but this is on an oceanic basin. Cause huge earthquakes. Subduction zones are really the culprit on huge tsunamis and huge earthquakes. It is very violent. Trenches. So back to what you could see here, the trench. It's very long, very narrow, very deep depression on the ocean floor, has very steep sides, and it's caused by convergent boundaries, subduction specifically. The deepest part is the Marianas Trench. It's also called Challenger Deep because we put like a aquatic robot, essentially a submersible, down in the ocean, and we called it Challenger, and it was able to go down there. It is meters, 11,033 meters deep. So I always show you the meter stick in my classroom, and that is 11,033 of those. If you want to convert that to feet, go for it. Oh, here you go, 35,767 feet. How many miles? Hold on, let me do some math real quick. You can just pause me for a second if you want. What do we say? I'll just use my calculator. Okay, so 35,767. Oh, you know the next conversion, I don't. 35,767. I don't remember how many feet are in a mile. I know you guys do. I know it's 2,000 or 5,000 or something. How many feet are in a mile? This is one of those 5,280. It's one of those conversions you don't have to know as an adult. Okay, 6.77 miles. It's almost 7 miles deep. It's pretty deep. That's pretty deep to continually be going down. It is pretty deep. Okay. I mean, I thought it'd be deeper, but whatever. And I mean, it is deep. What do I know? This is deeper than Mount Everest is tall. And this is deeper than the height that commercial airlines can fly. They can fly at 35,000 feet. So that would be about 6 miles in the air. Okie doke. The volcano will form when the opening in the crust will allow the gas and molten rock to escape out. Volcanoes rise above sea level to form islands like Hawaii and the Philippines. A volcano is just a mountain or a hill that has a crater, or it has like a vent in it. And that lava or rock fragments, really hot vapor, but really like volatile. That's what we're looking for. Really volatile substances are coming out. Acidic, sulfuric, very low in oxygen, very explosive, very dangerous. When this comes in the air and these super hot things explode out, these huge fragments solidify and come down as just huge boulders and are very dangerous. It's very dangerous to live by a place where the earth is wide open to you. It's very dangerous. Hot vapor, gas is all being formed from the Earth's crust. Many volcanoes are under the ocean, and they will form new seabeds when magma cools. Sometimes when you have a subduction zone and some crust is lifted, or some oceanic crust is lifting up, it does lift up these areas that did have magma solidified and was just a little bit too deep. There was one recently, and a new island popped up. That's worth me searching for it. So I'm going to pause you and come right back to this. Okay, back. I added just an informational slide about earthquakes creating new land. Anyway, it's in a couple slides. And then I got sidetracked and was reading about Freddie Mercury's life, but I'm back. So lastly, we were just mentioning the Ring of Fire in the Pacific Ocean. This is a very active tectonic area. Volcanoes can be found around these boundaries there. The crust is also very thin. And then it also can be found at divergent boundaries. So at the middle of our mid-ocean ridge, where it's spreading, we have a long underwater chain of volcanoes. Here's our Ring of Fire. These are big subduction zones. Right here, where we have this orange right here, is the San Andreas fault line. They're not super common just to have a fault line. We have one right here, moving, again, opposite directions, parallel to each other, but you're not really going to feel a bunch of earthquakes right here. It's not super inhabitable down here, Patagonia, and nobody's living over here. Little fault line, but nobody lives down there. Again, a fault line, but this is our biggest one is going to be in California, where most people can feel that fault line over here. But this is that's because it's part of that Himalayan mountain chain. We have convergence right on this part, again, fault line, and then earthquakes. Everywhere that's yellow are earthquakes. Very active regions here. Okay, and the Pacific is moving towards the Eurasian plate, while our Atlantic is moving apart. Earthquakes are going to be a sudden release of energy from the Earth's crust. This definition is important that you definitely include the word sudden or rapid release of energy from seismic waves, could be from tectonic plates or from volcanic activity, but it is sudden or it is rapid or it is quick. They're quick. Now it's a buildup of energy, builds, and then there's a quick, sudden slippage or sudden movement. Just to read this through, convergent or transformed plates can get stuck, right? Because it's not smooth. Like I said in class, it's not smooth. There is jaggedness to rocks. And wherever it gets stuck, it might be stuck there until pressure underneath from all of that convection movement from your mantle is enough that it just causes them to shift. Well, that energy that is built up, and that energy has to go somewhere. So it will be in the form of an earthquake. It radiates through the earth, kind of like sound waves. If you yell, that sound has to go somewhere. If you're in a small area, it's going to hit the walls and come back. This earthquake is happening underneath the crust and, within your asthenosphere, and that has to radiate up and out. There are different different types of seismic waves called S and P waves. I don't believe we're going to go into that. We aren't. Those waves travel at different speeds. They also travel through different types of mediums. So like a P wave can travel through everything. S waves can only travel through solids. Okay. Did I say that wrong? S waves can travel through solids. S waves can travel through liquids. Correct. Okay. Yeah, I was right. Can only move through solids. Okay, convergent, again, they get stuck. Your convergent or transform boundaries, all that energy is released. The store energy that's in the form of potential energy, write that down because it's not moving, it's not kinetic, it's building, 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 building. There's a question where potential energy could be a mark. So when we talk about earthquakes, we want to talk about high amount of stored potential energy and then the sudden release of energy. Okay, volcanoes can cause earthquakes, which can then erupt. What is that? Volcanoes can also cause earthquakes when they erupt, like shaking of the earth. What? Duh. The sudden release of energy in the seabed can cause tsunamis. So when you have an earthquake or from a convergent boundary or a transform boundary, in the ocean, that energy has to go somewhere, and it's going to be able to travel through this liquid medium, causing huge amounts of displacement. Huge amounts of displacement. If that's just take my word for it right now. If that's hard for you to understand, I will show you a good video that actually helped me have a better understanding of what is going to cause this, where we can actually see a graphic of the movement of the plate at the bottom of the ocean, lifting all of this water and causing it to move. Tsunamis have long wavelengths with high energy. Long wavelengths. That means your length between each wave, its peak or the troughs, or its crust, same thing as the peak. The distance between those two is very far. That means it travels very slow. They're very far. Here's a wave, here's a wave. And I mean, this is a small computer and I'm in a small area, but they're very far apart. But they have high energy. Again, the energy is all in the amplitude. The energy is all in the height. Doesn't matter about its speed. If it's carrying a lot of water, it doesn't matter if it hits you fast or slow. It's going to be faster than you can even plan for. The energy is all in the height, and we discussed that last chapter. When the earthquake releases its energy, it all moves into the water above the seabed. The water holds on to all of this energy and moves very quickly through the deep water. And they're also moving in convection circles. When that convection cycle in the water, moving energy through, cannot continue its ellipse, continue its cycle, and it starts to scrape or hit the bottom of the seabed, that's when we see this wave starting to crest big time. But all that water has to go somewhere, whether there's land there or not. Some countries will build tsunami barriers, big walls that can come up, or walls that are already there, or breakwaters to try and slow it down. But it's a oceanic amount of water. Excuse me, I'm sorry, I don't know, I'm yawning. As it nears shallow water, it will slow down, but all that speed now is going to be given to its height. So it's going to grow and grow and grow and grow. Whenever it's in the middle of the ocean, there's this huge depth of seabed where all of that energy can dissipate throughout, but that energy is still moving. When there's not a lot of seabed left, right, and we're deep, and then we get shallower and shallower, all of that water moving, if it can't continue dispersing the energy through the depth, right, because it's starting to curve back up your continental shelf and margin, it's going to be moving itself into height. The speed can't continue underneath, so it's going to lift itself and turn all that energy into its height, because the land is slowing it down. Okay, as it nears shallow water, again, it's going to slow down but grow in height. Another yawn. Tidal waves. We can call this tidal waves. Has nothing to do with tides. They're called tsunamis. Tidal wave. That has nothing to do with the tide. 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 It's all about tsunamis. This part right here, the sudden release of energy. How does a tsunami form? This is super important. So about having that underwater earthquake, underwater earthquake, underwater earthquake, large amount of energy being stored in the form of potential energy. Underwater earthquake, and then you have that energy released, travels through the water. When it gets shallower, it moves in height. It has that energy now transformed to height because it can't continue at speed because you're hitting your oceanic floor. This process, I know, is a question. Tsunami is a seismic wave created by an underwater earthquake. It's not a tidal wave, it's a seismic wave. It's made by seismic activity from plate tectonics, from an underwater earthquake or a volcanic event, not noticeable in the open ocean until it builds to greater height in the shallow water. We do have buoys offshore to measure if there is a huge height difference. And if there is a huge height difference, then you know that a tsunami is on its way. Okay, and this is the slide that I added. So earthquakes can produce new land, Pakistan, September 2013. I didn't put a video up. There are videos on, I believe, off both of these links. This is the new land that was created there. It was not there before. They did have a pretty big earthquake. It caused hundreds of deaths. But the first video that I came across was pretty biased, so I didn't put that in there. But you have an example from NASA, which is pretty cool. Like, this can happen, and then livescience.com. Click this link on earthquakes. Anything I have here, if it has an underline, if you want to just move your cursor over it and see if it's a link, it would be something I would show in class. I don't just do notes. I definitely also include a lot of videos. So your sudden release of energy inside the earth, it creates seismic waves, and it's from the movement of tectonic plates or volcanic activity. Anchorage, Alaska, a couple days ago, just had, at the end of last week, like Friday, just had a really big, I think it's like a 7.9 magnitude earthquake. It really did a ton of damage. Now, the earthquake did not occur offshore. Alaska is pretty vulnerable because it is at a subduction zone, and this is what caused that earthquake. Subduction zones cause the most amount of seismic damage. It didn't cause a tsunami. They were concerned about a tsunami, but it did not cause a tsunami because this earthquake happened on land. Yes, the land was close to shore, but that energy was able to be dissipated through the land structures and not transferred all into water. Underwater earthquakes are going to cause your tsunamis. Okay, again, tsunami video, and I'll show you one in class. I'm not this is not the same one that I saw before. Okay. Tsunami video. It's a seismic wave created from an underwater earthquake. Underwater earthquake. Underwater earthquake. What kind of earthquake? Underwater. Yay. Underwater earthquake. Underwater earthquake. An underwater earthquake. Earthquakes can be caused from subduction. Could also be caused by, and that's convergent boundary, transform. Underwater, though, and all that energy gets moved. Where if it occurs on land, you may have landslides, you're obviously going to have building damage, et cetera, but it's not the movement of water, it's movement of land. Okay, it's often not noticeable in the open ocean, but it'll build to great heights when it gets to shallower water. It does not look like this one at the bottom, even though that's like the tsunami of my nightmares. That has been less frequent, though, because I know this is not what it looks like. This is not what it looks like. This would be like 1,000 feet, maybe 1,000 foot. That wouldn't happen. It's taller than these buildings. It's crazy, but it's not true. This one too. Not true. Divergent boundaries. Here's the picture from our mid-ocean ridge where it actually is spreading. Okay, divergent boundaries. These are going to be areas where they are diverging or moving apart, and molten magma is going to come through it and resolidify. These are also called constructive zones because we are constructing new land. Like, we're constructing something, we're building. Whereas convergent zones, where we ran into each other, we're destroying each other. And so we call those destructive zones. And as magma pushes through the Earth's crust because of your convection currents, again, it spreads and solidifies at the bottom of the sea. The bottom of the sea is really cold and the pressure is really great. So as soon as we have a little bit of really hot, liquid magma, it's going to just be solidified. But we do have that area where it's thin and it's going to keep coming out. The new rock builds up and it'll form underwater mountain ranges called mid-ocean ridges. The ridge is going to be like the height right? It's gonna come out and then like solidify, come out and solidify, come out and solidify. So that ridge is the height. Whereas in Africa, we call those rift valleys. It's rifting apart. There's not a ridge there because it's not magma coming out, it's water filling in. So mountain range with a central valley on the oceanic floor at the boundary between two diverging tectonic plates. So plate diverging, so they're moving apart. And we have this really deep valley where magma's coming up and building new crust. Magma's coming up and building new crust, but they're moving apart from each other. This is also called seafloor spreading or seabed spreading. The split in the ocean, they split the ocean and it pushes them to different ends of our planet, and it will also be closing up another ocean. I want to read the bottom, but that's cut. Pacific Ocean is shrinking, Atlantic Ocean is growing. In a mid-ocean ridge, there's volcanoes and there's hydrothermal vents. Transform boundaries, these are where the plates are going to move side by side to each other. I don't know what time I'm at, doesn't matter. They're going to move side by side to each other. So when two plates slide laterally next to each other, they create friction between them. No crust is created and no crust is destroyed in a transform boundary, but it's a lot of seismic activity. This was the example of you rubbing your car up against another car or a drive-through or a gas station. It's going to create a lot of friction and build up a lot of pressure. And whenever that pressure is too great, those plates can actually move, can cause an earthquake. If it's underwater or if it's really close to water and land, it can displace that and cause tsunamis. So underwater earthquakes, again, can be caused by transform boundaries, by convergent boundaries. Those will lead to tsunamis. If it's on land, then you are going to have just more land damage than you are going to have water being moved. The friction will create really small faults, really small cracks in there. The pressure can form like the pressure along a transform boundary. You can see this abyssal plain that is there. Abyss, if you're down into the abyss, that's the bottom. And a plane is flat, a flat surface. Okay, the most common feature that you can see is an abyssal plain when you have a fault line, a transform fault line. These are also called conservative boundaries because they're not creating, they're not destroying, they're being conservative. Okay, and we have this between the Anatolian plate and the Eurasian plate. Abyssal plain is a sandy flat region on the ocean floor between the trenches and the continental rise. All right, so here's our shelf. Slope, very steep sloping, very steep sloping. Continental rise is next to our abyssal plain, next to the abyss. So this area right here is going to be like part of the continent, part of like the continental plate, whereas the one at the bottom is going to be your oceanic plate. We can have sea mounds. Those are your dormant volcanoes. We can have volcanic islands. You can have a rift valley, or they can create ridges. Oops. Over here, where we would have a trench. So this would be because this plate here, this oceanic plate, is subducting under this continental plate. Continental plate's much thicker. Okay, it's creating a trench. Over here, we would definitely see volcanoes and earthquakes and even tsunamis on this island. And I know that because of the trench, because a trench is created at a subduction zone. Again, continental, this is the abyss, the abyssal plain. And then we have the continental slope, where you have a very steep sloping like gradient. The continental shelf, where it's more flat. This whole continental area here is going to be called the continental margin. Hydrothermal vents. We've talked about this in chapter 2. We have talked about this in chapter 3. Surely we've talked about it in chapter 4, and we talked about nutrient cycling. So this was, again, discovered in 1977 when we just really thought that the bottom of the ocean was nothing. So this was in the Galapagos Rift in the Pacific Ocean by scientists from the Woods Hole Oceanographic Institute. They were using the submersible name called Alvin. They found mid-ocean ridge systems. They found pressure over 200 atmospheres. And again, we live at 1 atmosphere. We have 1 atmosphere above us. So this would be 200 times the pressure that we feel. There was no light. And they were like, well, we're in a really high pressure area. There's no light. How is anything able to live? How do they form? So there are questions that say, explain how seismic activity can give rise to hydrothermal vents. How long has this been going on? 1 hour. All right, let's try and keep going. Here we go. How do they form? Cold water is going to fall into the cracks of the crust. So first, it's water from the ocean going into the earth. It's not earth coming out yet. It's water from the ocean going into the earth. Because there are cracks in the crust. There's little vulnerabilities. There's little areas of weaknesses going to the cracks of the crust. And this is going to be through like a divergent plate boundary. This is for your hydrothermal vent. So like mid-ocean ridge. The water that will flow, the water that's going into the crust is going to get into like a magma chamber. So like into here, water is going to be flowing through. Water is going to be flowing through these little divergent boundaries where we're rifting, where we're breaking apart. It's going to be falling into this magma chamber. And it says percolation, like drip, 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 drip. That's percolation. Drip, drip, little percolations. Drop, drop. Like if coffee can percolate. Drip by drip by drip. It's the best kind of coffee if you have like a percolator. Anyway. Water is going to flow into the crust of the magma. And now it's going to be really hot. It's going to dissolve iron and copper and zinc sulfides from this actual crust, from like this harder like rock material. It's going to make the water black. That's why we call this black smokers. The water will get super heated. So first we have water sinking through. Then we have water dissolving really heavy minerals and volatile minerals. And then it's going to get really hot because now it's like by magma and it's near the mantle. It's going to reach well over 100 degrees Celsius, which is well past boiling. However, the water can't boil. Yes, it's very, very hot, but the pressure's so high, so it keeps that boiling down. The water is still that hot. It's just not boiling. It's not changing its phase. It's still that hot, but it's not changing its phase. The superheated water will escape from these cracks here. Why? Because hot things are less dense and they rise. The same reason why things are moving, in our homes, in our coffee cup, in the ocean, inside of the earth, are all because of the same things, because of density and differences. Less dense things are, the things that are less dense are warm, they're porous, they don't have a lot of particles per area, they don't have a lot of dissolved particles inside of them. Things that are very dense are cold, very solid, lots of particles per area. Again, something to think about, like a brick and a sponge could be the same size almost, but a brick has more particles per area than a sponge does. So the sponge will obviously be less dense. So the superheated water is going to escape from these fissures. Then what? That superheated water is going to be like really close to super bottom of the ocean and super cold water. So with that dissolved particles, it's going to cause these particles to solidify within their solution, and that's called a precipitant. In 9th grade or in 8th grade, when you guys do physical science, you should have talked about a chemical change. You know that there's a chemical change happening because it could cause a color change. It could cause a change in state. So solid, liquid, and gas is a physical change. It could cause a color change. It could cause gas, not steam, but gas to be formed. And it could also cause the formation of a precipitant, which is a solid coming out. You can make a precipitant if you guys have milk or coffee creamer and you mix it with any kind of alcohol or soda. It'll start to coagulate and it'll start to curdle, and that is a precipitant. Okay, so the minerals will precipitate out and they're going to solidify and top each other. And this is what's building that actual vent, that actual like plume that we see right here in our picture. It is just from these minerals being super hot and then coming in contact with something really cold, and they're going to solidify. So it'll cause a vent or a chimney from the water. Can be really high. Can be how high? It says meters high. I'll have to read the book. It could be high. 10 meters high, possibly 20. Let's find out. 60 meters high. That's like 6 stories. The water will be released at over 350 degrees Celsius, but it's not boiling. It's really hot. Can't boil because of the pressure. We can call these black smokers, and the chemicals that come out from the crust are the basis of chemosynthesis, like all these little sulfides, iron, coppers. Okay. We need to know how our tectonic boundaries, like this divergent boundary, can give rise to hydrothermal vents. So I gave these to you in certain steps and in like bullet points because I know you need to be able to go through that outline. All right, our seabed. Okay. Within chapter 6, there's 7 sections. This is the 5th section talking about the different areas of the seabed. So the ocean is divided into specific regions depending on where they are and what structures they have. The continental margin will include these 3 things: the whole area, the whole margin. Like in the margin of your paper, you might have your name, the date, the period, and what class you're in. So that margin is going to contain all these different aspects. So the continental margin can be thin and dense oceanic crust from the thicker continental crust that is less dense. So it can have like the edge of continents and then ocean on it. Definition of continental margin: it's the submerged area next to a continent, which includes the continental shelf, the continental slope, and the continental rise. The continental shelf is, think of a shelf. It's flat. We stack things on it. It's flat. It does have a slope, but it's a very small slope. Flat area extending from your shoreline to the big continental slope where we actually like drop off. It's featureless because there's a lot of high wave action and there's a lot of sediment deposition. Lots of wave action, lots of sediment deposition. By featureless, like there's not a trench there, there's not a volcano there, there's not a mountain there, there's not an abyssal plain. Continental slope is going to begin where the shelf ends. It's very steep and it just sinks right down to your ocean basin. It's even steeper when you're near a convergent boundary where there's trenches. We'll look like this one right here. Here's my trench. This is very steep. This steepness, this slope would be way more steep than what's going on right here because of this trench, because of subduction. Continental rise is this narrow or this thin edge. It connects the slope to the seabed. This is where your sand is going to deposit. It's small, your continental rise. So if we're going from the seabed, it's the seabed or the abyssal plain if you're at a transform area. And then we're going to go the continental rise as it starts to move up. The very steep decline is called the continental slope, and then it's going to lead to your continental shelf where we're going to have a lot of our wave action, et cetera, and then we're going to hit our shoreline. After the continental rise and abyssal plains, after the continental rise, after the rise, like I said, is the seafloor or your abyssal plains. They're very flat. They make up 50%, more than 50% of Earth's surface. They're found between your continental rise, so that tiny little narrow area that starts to increase, and your mid-ocean ridge. They're formed in rocky surfaces of the seabed, get covered by depositing sand and by depositing organic material, which we call marine snow. Told you to draw this. Many of you did. Some of you decided that you don't need to draw what I tell you to draw. I did not see it in your notes. Of course, there's different instances, but many times this is the difference between a C or a D or an A or a C. You have to have pictures with this. I'm not telling you this because I want you to do more work. I just want you to be really good. And what I'm doing is trying to get you there. So if you didn't draw this, Do me a favor and draw it. Thanks. All right, so here's our shelf, and here's where we would be playing, right up here in the corner. Here we are. I guess your sea surface. Well, here we are, right at the surface. Here we are. Continental shelf. Again, it's relatively flat. Big fall. So this whole edge right here, I would, put a color on it, but I know that color is going to stay throughout the entire presentation, which is annoying. This steep fall right here is going to be the edge of our continent. Florida would look like this. Florida. So if we go off our continental shelf, boom, we just fall. And this would be the edge of North America. We go down to the abyssal plain, and now we're like at the bottom of the Atlantic Oceanic Basin. Okay, so, and again, continental, different plates, depending on what it is for your plate tectonics, can be just continental, just oceanic, and it could just be like this tiny little area inside the ocean, this little area, or it could be oceanic and continental. It really depends on where that break was caused. Again, really deep continental slope, the edge of our continent, continental rise, even though it doesn't look like there's any sort of like decrease in slope, there typically is a decrease in slope in the continental rise, and this is where all of our sand is going to accumulate in marine snow. And then we have this flat abyssal plain at a convergent boundary where there is subduction, and in this picture there is. We have this huge plate. No, this is going to be my continent. So this plate, my oceanic plate, is more dense. It's going to sink underneath this continental plate. Okay, so if I'm looking right here, I can show you the density. And you guys should already have this in your notes, so this shouldn't be different for you. And I'll go back to that previous slide. Continental crust is 2.7 to 3 grams per cubic centimeter. The sediments on the shelf, on the continental shelf, are 2.3. So they're going to sink. And the oceanic crust is 3 to 3.3. So just looking at 2.7 to 3 or 3 to 3.3, continental crust is less dense. So it will stay above your oceanic crust. All right, so if this is trench forming, trenches only form at subduction zones, then this is my continent. My continent is going to be less dense. This is going to be the floater. This is going to be the sinker. So it's moving underneath, causing this huge trench to be created. And once this huge oceanic plate moves underneath, that friction is going to increase a lot. It's going to cause melting of this oceanic plate right here. The melting is going to make it liquid, and it's going to be liquid rock moving up, and it's going to break through the crust and make a volcano. Okay, isostasy. That's not how you say it. Isostasy. It's isostasy. I don't know where to put myself. Can I make me smaller? Oh, a little bit. That's fine. Okay, so ISO is the same and Stacy is waiting. Why would anybody name their daughter Stacy if it means weighing? I don't know. Whatever. It's fine. Isostasy. It's very similar to buoyancy, but this is related to Earth's crust floating on the mantle. Earth's crust is less dense from the mantle. How do we know? It floats on it. If it's floating, it's less dense, has less particles per area. That's why I put our mantle in bold here. The mantle's density, even though it's liquid, it is also very hot. Even though it's very hot and it's very liquid, liquid things are less dense than solids. Hot things are less dense than non-hot things or than cooler things. So everything with those two ideas, the liquid, so the state that it's in, and its temperature would make you think, well, why doesn't the mantle float on top of our crust? But that's because the mantle has an incredible amount of pressure. Just pressure from gravity, just pulling all these particles in. And that pressure is going to keep it more dense. Particles per area. Yeah, there's a lot of kinetic energy. There's a lot of heat. There's a lot of movement. It's a liquid state, but it's just very compact. Okay. So continental crust, 2.7 to 3. Oceanic crust, 3 to 3.3. Continental crust is less dense, has less particles per area. Yes, it could be thicker because it has mountains on it, but it's not as dense. So continent will be on top of the oceanic crust or float on top. Both of those things are more dense than the mantle. Even though the mantle is hot and the mantle is liquid, it's still going to float on top of it because of a density difference. So in geology, isostasy is going to refer to how buoyant different rock layers are, and this will allow them to float on different layers of other rocks. The buoyancy of each rock is determined by its density and thickness. This is why Earth's crust is able to float on the denser molten rock of the mantle, or how ice floats on water. Again, ice is the water, H2O, is the only molecule whose solid will float on top of its liquid state. This will allow scientists to create a model of the Earth of why these rock layers or these continental layers or even oceanic layers can float on top and not sink back in. Both continental crust and oceanic crust are less dense. They're going to float on the mantle. Continental crust floats higher than oceanic because it is even less dense than the ocean. Though it's thicker, it's less dense. Here we go. So we can see it floating. All right. The idea that lighter crust must be floating on the denser underlying mantle. So in the last ice age, most of the planet's water was in the form of ice, and that lowered our sea levels. Although all the continental shelf regions were above water, most of our shelf regions were above water, which is kind of cool. So the continental slope and continental rise, like that may have been like one of the first things that you would have seen then. This part, they're saying right here, this 200-meter mark, this part was exposed. So it's very exposed. So you can kind of just drop off into the ocean and not really be able to like play in a tide zone. Most of all of our continental shelf regions, again, were above water. Now the continental shelf forms at the bases of shallow seas and edges of the continents. This is why our continental shelf is relatively shallow, and it's covered in sediment because of erosion in the rocks on the continents from the previous ice age. There's a question about shallow seas and isostasy. We'll need to also talk about ice ages and water melting. Water depth is controlled by the changes in sea level from the melting or freezing of ice. It's also going to be controlled by isostatic changes, or the changes in density and the changes in buoyancy of your rock. If something becomes more dense, it's going to be heavier and sink more, and that's going to cause your surface, your sea level to rise. If it's going to lose density, it will allow it to float more, and your sea level will get shorter. So we'll go glaciation periods. The littoral zone. Click this link, and you can watch about the littoral zone. So the littoral zone is going to be the bottom, or in ocean terms, we say benthic. Benthic, benthic. So it's the bottom zone between where your high tide is and your lowest tide. So it's the area that is going to be exposed when your tide goes out, and then the area that gets covered again when your tide goes in. So it's also called the intertidal zone. So littoral zone and intertidal zone are, really used synonymously. Inter means in between. And then tidal is tide. That's dependent on our moon, our lunar phases, which is chapter 7, next chapter. So inter means in between, and then tidal zone. So in between the tides. We have a high tide, and then it goes back out to low tide. What is in between those? So that's the littoral zone. It's going to be the area of shore where land is going to meet the sea, also called the intertidal zone. This is the area between your high water mark during a spring tide. A spring tide is when you are going to have the strongest tidal pull from where your sun and where your moon are. A neap tide is going to be the opposite. I don't need to talk about neap tides, but spring tides are the biggest. Have nothing to do with spring, have nothing to do with spring, have nothing to do with spring. Nothing to do with the spring tide. Yeah. So this is the area between your high water mark during spring tides, and this is where the pull between the earth and the sun are going to be the moon and the sun are going to be the greatest, and the lowest part that's always submerged. In this picture, The tide is out right here, and when it comes in, it goes up this whole area. Now, intertidal zone is different based on different shorelines and different morphology. Areas that have subduction and convergent boundaries have rocky shorelines because you have a lot of volcanic activity coming out and creating a lot of rock or scraping against continental plates. This area is going to be categorized according to the shape of the shore, the amount of wave action it has, or the erosion. The substrate that's going to make up the shore, so is it rocky, muddy, sandy, and the organisms that live there. The shape of the shore will depend on the geology of the land. So again, is it a rocky shore formed in a subduction zone or a convergence zone? We don't have any kind of plate tectonics by our area, so we have this sandy shore. So that's really what's going to depend on what's going to determine what kind of shoreline or what kind of littoral zone or kind of organisms are going to be there. How much erosion it's exposed to. For flat land with fine particles or mud on vertical rock cliffs, those are going to be things that are going to define what kind of area you're in. Morphology is the study of the formation of things. That is the textbook definition. So ology is a study of, and morph is how they morph. So morphology, or how things are going to move on and grow and form, is going to be dependent on the size of the sediment that's there. And on page 108 in your textbook, I'll show it to you, and then it's going to be backwards, so I'm going to flip the screen. The size of your sediment, and then the slope of your shoreline. Okay, flip the screen. If you want to pause it, I do want you to have this. I did mention that in class. Hold on. Okay. If you want to pause it, now would be the time to pause it. Pause. All right. So silt is 0.002 to 0.02 millimeters. Luckily, all these have, a 2 in them. You can remember silt, it will be the smallest part. It's either going to be, it's 0.02 and smaller. 0.02 and smaller. Fine sand is going to be 0.2 to 0.02. Coarse sand, 2.0 to a 2. And then gravel or small stones are going to be greater than a 2, which would be like our rocky shore. So it goes 2 to 0.2, 0.2 to 0.02, and 0.02 to smaller. 2 to 0.2, 0.2 to 0.02, and 0.02 and smaller. All right, the different types of seashores, morphology, yay. We did talk about this last week a little bit. Rocky shores are going to have a rocky substrate. They're going to vary widely in slope. You can see this variation in this picture. Still a rocky shore, huge slope. Rocky shore, not as great of a slope. You can have rocky shores where there's also sand and a very small slope. Rock sizes can vary from large boulders, and that's also called moraine whenever it's the result of like glaciers scraping against rock, to small pebbles. It's going to be granite or igneous rock. Igneous rock is formed from your solidification of lava. These are really resistant to weathering, really resistant to erosion. So yes, rocky shores have very high erosion. You would imagine that it would be broken down in tiny particles. However, rock is very resistant to weathering. Shells and silicates are not resistant to weathering. And that's our sandy shore. Your largest rock, obviously, is going to be furthest away from the shoreline. It's going to help be a breakwater, and that should make sense. The biggest rock is not going to be carried as far because it's more dense. So it's going to be stuck further out in the water. Now, if you have water that's really strong, it can pull that rock even closer. But the lighter rocks are going to be easier to be moved forward. The heavier ones are going to be out in the back of the intertidal zone, hopefully acting as a breakwater. This is most exposed to erosion because your wave action is constant. But it's also the most resistant because it's made of granite and it's made of igneous materials. Sandy shore, made of loose sand like silicates and pieces of gravel and shells. The sand is actually formed by erosion of your sandstone and by the waves just constantly crashing them, and the waves are depositing the sand and the sediment. The sediment's really light, so it can get carried through the waves and then dropped off onto the beach where we're sitting. On a rocky shore, those sediments are not very light. they are not going to go very far in the water. And you can see here, like some of these rocks were deposited before they even made it to the intertidal zone because they're heavier. Sandy shore, a piece of sand is not going to be like zoop, sinking right to the bottom. It's not that heavy. It's going to be able to be suspended in the water and taken up to the shoreline. These particles are always in motion. Sandy shore is always in motion. The erosion isn't as high as your rocky shore, but the sandy shore is way more exposed to erosion because of what it's made of silicates, sandstone. There's a gradual slope that moves towards the ocean. So erosion is the process where we're going to wear away at material and transport them. Deposition is going to be where we're adding, where we're depositing onto. So we erode our bank account whenever we spend. We add and build in our bank account whenever we deposit. Right? And then when we erode it, we're spending it somewhere else. Different types of seashore morphology. Continuing. So we just did rocky shore and sandy shore. Estuaries, super important. They're awesome breeding grounds. They're a nice in between being in a river that's freshwater and an ocean that's saltwater. They are not exposed to wave action like the intertidal zone on our shorelines. A lot of organisms are coming into our lagoon to lay their eggs, to have their pups, to have their babies. The water will stay warmer there than it will in the ocean. The water is much more consistent there than it is in the ocean. They are not susceptible to waves. They're not susceptible to as great of storm damage like you would be in the ocean, and they're not susceptible to tides. So it's a partially enclosed tidal body of water. These are also called bays. So the Bay of Fundy, San Francisco Bay, a lagoon, a sound, a slough. Sloughs are usually used more in Europe. So enclosed body of water, tidal body of water. And the tide is what's going to push water from the ocean closer to the river, the lagoon. And fresh water from rivers are moving into lagoons. So when the tide comes in, we're going to have a lot of saltwater input. Fresh water is coming in just from the middle of the state in all parts where we have fresh water and lakes. And then the ocean is coming in whenever we have tide changes. And that's a mix. This mix is called brackish. It's sheltered from erosive waves. The bottom is fine sand and silt. So sand and silt, so 0.02 and smaller, and 0.2 to 0.02. When the water is calm, all those particles will settle out to the bottom. If it is stormy or high waves, or let a runoff, the water can become murky and turbid because of these sediments. Muddy shores are found in protected regions. They're the least exposed to erosion. They have the least amount of water input. There is no slope. That's why we call it a mud flat. There is very little water movement, so erosion is extremely low. But deposition is very high. We are having a lot of things depositing. A lot of sedimentation, a lot of deposition. It's very high. A lot of sediment is silt, tiny little particles that are usually constantly suspended in water whenever we're in the sandy shore. Constantly in motion are not in motion here because of the erosion. There is no erosion there. And then your book talks about deltas. Deltas make a delta, and in class, that's what we have her change in. It's a delta, the Greek letter delta, looks like a triangle. They also make this triangular shape, and we call it a delta. This is a low-lying triangular area at the mouth of a river, and it's formed by the depositing of sediments before this river goes out into a bigger body of water. Our Mississippi River Delta Basin is huge. It even comes from the Great Lakes. And there it is. It's making this triangular shape where it comes to this this V, this peak at the end. Okay, it's going to be where river meets the sea. It's named after the Greek letter delta. The river flows towards the mouth. It picks up sediment. And it's going to be moving faster and faster and faster. The river begins to widen as it approaches the sea. And we can see that definitely towards the end. It is getting thicker and widening towards the sea. This widening will slow down the speed of the water, and it allows your sediments to go to the bottom. It's not as rapid. When it's moving in a greater area, now it has more area to cover. It can't move as fast. Same thing with our huge tsunamis. big area to cover, very deep area, it's moving slow. As that area starts to slope up, it doesn't have to cover as much area. It can increase its speed turns into its height, essentially. Okay, so the widening towards the end will slow down your seawater, and that allows the water to be a little bit more calmer and allow particles to settle out. Sandbars form over time, forming a wide fan shape, and it resembles a branching tree. You can build new tributary channels out of this. The Mississippi River Delta will drain to the Gulf of Mexico. Our Nile River Delta will drain to the Mediterranean Sea. I saw this. Hold on. I don't know. Okay, I deleted it. When Olive and I were going to Texas, we were flying over Galveston Bay. It would be way over here, but Galveston Bay has a lot of rivers flowing into it, and from the airplane you could see it looked just like this murky, different sedimentation color of water, and that is just a ton of deposition, ton of depositing. Okay, the Nile. And you can see this as it widens, it slows down, and it has time to deposit all the sediment that it's picked up. Three kinds of ecosystems in the littoral zone. So we're going to talk about the rocky shore, where it's in, three kinds in the rocky shore. So we're going to look at the high tide zone, the middle tide zone, and the low tide zone. This is just about the rocky shore. So they are going to be biotic and abiotic components. So we need to consider when this water is moving, are they going to be exposed to different temperatures, to air exposure, to substrate being moved, to salinity changes. So in a rocky shore like this hard, you're going to have a lot of fluctuating temperatures, heavy wave action, exposure to air whenever the tide is out. You have to be able to adapt to the slope of the shore, whether you have a very great slope or a very small slope. You have to adapt to the type of rock that your substrate is. If the habitat is tropical or temperate regions, if you're going to have sunlight availability, if the temperature is going to change huge, or if the salinity is going to change huge. They also have a lot of biodiversity because we have a lot of organisms who can and will adapt to this area because we have niches, we have productivity, we have substrates for our producers to grow on, so the rest of the food chain can come. So the rocky substrate will allow organisms to attach to it. Can have seagrasses and major producers like that in a sandy shore because no substrate. Anchorage is a necessity. You need to be able to have space to anchor on, and that is going to be the biggest competition component. Not food, but do you have space to anchor? So to limit this competition, organisms are going to put themselves in an area of zonation and space themselves vertically. Some organisms will be really good to be adapted for just being underwater. Some can do underwater and air exposure. Some can do just big air exposure. It's called zonation. So separation of organisms and a habitat into different zones or bands according to the biological or their physical factors. This is very common on a rocky shore habitat. In a sandy shore habitat, this is not as common because you don't have very many different habitats. You got to be a burrower, period. That's it. A species zone, so what zone they can live in, because we're going to be looking at the high tide, middle tide, and low tide zone. This will be dependent on the temperature tolerance of the organism. How much time can they stay out of water before they dry out or they desiccate? Do they have competition between other species, or is there going to be heavy predation if they're out of the water or if they're in the water? All right, your high tide zone. They only have water during high tide when the tide is up very high. So they need to be able to adapt to long periods without food, without water. They could dry out whenever the tide moves back. This is going, so in a high tide area, I'm going to show you pictures so you can imagine. Olive's awake. Sorry. Darn it, why is she awake? High tide would be like up here. No, you can see it right here where the water comes. That's your high tide. This is low tide. I had so many hopes and dreams for myself. I was planning on her sleeping at least another hour. All right, let's try and finish. What slide am I on? 36. We can do it. She'll talk to Moana. So these guys are going to be exposed majority of the day in the high tide area. So only when tide is high are they going to be underwater, and the majority of the time they're open. This is going to be chiton, Chiton. It's chiton, not chiton. Chitons. Chitons, crab, isopods, barnacles. Great. Your middle zone. So they are going to be exposed to air twice a day at low tide. So when the tide goes out, they're going to be exposed. So they need to be able to adapt to desiccation. They're just not going to be as exposed as long of a time as your high tide zone organisms. They are going to be covered a little bit longer. These will be limpets. Okay, limpets we saw in the picture in the video. Here it is, has this like conical shape. Limpets, periwinkles. These are little periwinkles, and then mussels. Mussels can close their shell. All of these guys, what they have in common is definitely a shell. This is a quadrat. Okay, this is a quadrat. It's made out of PVC piping. It definitely looks like it is half a meter or a full meter squared. Okay, the low tide zone. They're going to be underwater all the time, except whenever the gravitational pull from the moon and the sun is the greatest. Then it's going to like suck out water even more. So these guys are definitely going to have to stick into their rock pools. There are very few adaptations for living out of water. If they do come out of water, they definitely could die. They're not supposed to come out of water. They could overheat easily. They don't have shells like your sea star, your sea grasses, your urchins. They don't have shells to keep themselves moist and damp. They could dry out easily. So seaweeds, algae, sea stars, sea urchins, sea anemones, oysters. Yep. The tide pools can exist in each of these zones. Tide pool can be in here. Tide pool can be in here, and the water gets caught there whenever the tide goes out. And this will just allow them to have, some sort of coverage and some sort of water protection so they don't dry out. These areas, these tide pools, because they're constantly being refreshed by water as the tide comes in and out, we can have oxygen and maintaining a salinity constantly. And the water is going to just keep getting reoxygenized by fresh water coming in. If there wasn't fresh water coming in, the organisms in the water would use it all up in respiration, and then they would suffocate themselves. So we can, just looking at this picture, we can see a definite body plan. If you're going to be an organism more exposed to a high tide area, and then when the tide goes out, they're going to be out majority of the day. They're going to need to be burrowers, definitely have shells. Again, we have burrowers and definitely shelled organisms right here. As we go further down, we're going to be least exposed to tide changes, and these are going to be organisms that can have shells but also soft bodies. I'm just trying to motivate myself. Sandy shores. So we just looked at three kinds of ecosystems in the rocky shore, the high tide, the middle tide, and the low tide zone. Now we're going to look at different types of ecosystem in our sandy shore. Sandy shore, they have to adapt to a changing substrate. Their substrate is constantly moving. I believe these are pieces of sand deposit that a worm left out as the worm dug into the sand. Cool little formation. It's not an extreme environment. It is a very unstable environment because waves or wind can move your substrate. Yeah, not even just waves, wind. There's been plenty of times I've been pelted before at the beach and I'm like, yeah, I'm going to leave. I'm not going to be assaulted on the beach today by pieces of sand. Organisms must live in the substrate, inside of it. Those are in fauna, not outside of it. So organisms that are burrowers are also called in fauna because they're living inside the fauna, inside the sediment. Excuse me. Ghost crabs, cockles, little shells. Here's your cockle. Cute. Bivalves. Bivalve. Bi is 1, 2. A valve is going to be something you can close. So shelled organisms. Ragworms. Lugworms. Don't just say worms. If you want to have a specific organism, we need to know their names. You can't just say worm because we do have earthworms and they don't live in the sand. There's definitely a lower biodiversity than a rocky shore because of a very changing substrate, and you have to be able to adapt to burrowing. I don't hear Olive talking anymore. Awesome. So the sandy shore. We do have some vertical zonation, but they're pretty much all burrowers. Vertical zonation patterns are like the rocky shore. This habitat is going to depend on, are they going to be preyed upon by like birds or by, other organisms living up here, by a ghost crab? How able are they to resist desiccation? The zonation is definitely less noticeable because the organisms are burrowing and there's very low biodiversity here. So there's not many organisms to be in a zonation anyways. The only producer is going to be phytoplankton. It could wash up with the tides. It's just going to be planktonic floating at the top of the water. That is your only producer. It's not enough. It is not enough. It's enough to stabilize zooplankton, but it's really not enough to have larger food chains follow. And you can see that because we don't see a very biodiverse shoreline. We'll have sharks, dolphins, and turtles, but it's not what we would call biodiverse. Most organisms are detritivores, and they're going to eat organic material between the sea grains or pieces of organisms that have washed up and decayed. Detritivores. Worms, insects, crabs, isopods, all of those are going to be detritivores. Okay. Mangroves. 2 more slides. Yes. So again, what we were looking at, just so we can be sure, is looking at the littoral zone. The littoral zone is your intertidal, okay, between high tide and low tide. We looked at the rocky shore. They are very stratified and zoned. They have a lot of habitats they can live in. A sandy shore, they have this. It's just not as obvious because they have to be burrowers, so we don't see it, and there's not a lot of biodiversity. This is what your zonation pattern will look like. Definitely way less than the other one. All right, now our mangroves. Mangroves are going to be trees that can live in coastal or estuarine environments. They can also live in mud. They are between 25 degrees north and 25 degrees south. So they're growing in coastal environments, warm environments. Okay, these are mangroves. Mangroves allow for huge biodiversity. There's more than 110 different mangrove species. Many of them are found in Indonesia. That's where our biodiversity of mangroves is going to be the highest. They live in saline habitats because there's a lack of competition. Not many organisms can live in salt because they're going to lose all their fresh water and then dwindle and die, but there's a lack of competition, so they're like, well, yeah, we'll take it, and they have an adaptation. They have amazing biodiversity. They are amazing nursery grounds for other organisms. They can live in swamps. They can be mangrove swamps, mangrove forest. Our lagoon has many mangroves. You can have mangroves living in mud. There's 2 factors that will definitely impact their survival. The amount of salt that is in the water, and then the amount of oxygen that's in the mud or in the substrate, in the swamp, in the forest, at the bottom of the lagoon. So the amount of oxygen available. Oh, she's crying again. Okay, I'm going to finish the slide and then go get her. So let's see. Let's look at this next box first. So the saltwater content. Red mangroves will have 2 methods for living in saltwater. First of all, in biology, we talk about semi-permeable membranes. Our cell membrane is semi-permeable. Some things can come in, some things can't come in. Water is a barrier. Water is not allowed through the cell membrane unless it goes through an aquaporin, which is a protein on your cell membrane, because the cell membrane is made by a lipid bilayer that is hydrophobic. Lipids are hydrophobic. This should all be reviewed. So those roots are impermeable. They have a very strong cell wall. They will not let water cross through. Water would like to cross through because it wants to go from a high concentration, which would be, the actual environment, the actual mangrove, the water that's living in, to a low concentration, which would be the inside of the mangrove, but it's impermeable to that, so it does not let salt come through. That would cause it to become very dehydrated. They have sacrificial leaves for water that does pass through. So this is pretty cool. They will take all of the salt that's passing through and incorporate it into just a couple leaves. And it's not going to hurt the entire plant. They're kind of just, taking one for the team. Be like if every bad toxin that we came through could get stored in like our pinky finger. And then, after we've had so much toxin, we could just drop that pinky finger and then regrow a new one and then store all the toxins there. Black mangroves can expel salt through the pores underneath their leaves. How fun. So red mangroves, their roots are impermeable, and if salt does get through, then they're going to send all that salt to a sacrificial leaf and then drop that leaf. Black mangroves, they will expel salt from underneath their leaves. Anoxic soil. Remember, anoxic means lack of oxygen. Red mangroves will also use prop roots to hold themselves above the tide line and to absorb oxygen. Looks like this. Okay, absorbing oxygen. Also these guys, prop roots. They're propping them up, and the bark that's lining these roots are absorbing oxygen. Prop roots will hold up the tree. They're also going to hold your sediment in place. It reduces erosion. Could also be a breakwater for storms and hurricanes and reduce the wave energy. Black mangroves have pneumatophores that act like snorkels, and they stick up out of the water. This is our black mangrove, pneumatophores. Red mangrove. Red mangrove can send all of their salt to a sacrificial leaf and drop the leaf, but they also have really impermeable root systems that stop salt from coming in. They have prop roots that hold them up, anchor soil down, and allow them to extract oxygen. Because if they are the main producer in here, then they're not getting oxygen from the water. They're producing oxygen. So oxygen is able to be dissolved in the water too from their photosynthesis. Black mangroves. They have pneumatophores that will absorb oxygen from above, kind of like a snorkel. And they also release the salt that gets into their organism through underneath of their leaves. Algae, oysters, sponges, crabs, barnacles, fish, and other crustaceans live among the roots. Mangroves are a keystone species. Mangroves are awesome. Anchoring soil, stopping erosion. Many organisms will lay their eggs within these mangroves because they're protected. They have oxygen. They are protected from being eroded away. They may be protected from predators. And then when mangroves drop their seeds, the seeds are called propagules because they're going to propagate another organism. When they drop their seeds, they can float around for a period of time. Each species has a different period of time that they're floating around. They can rest on an area of, they can rest on land or where there's a lot of sedimentation. So there's a lot of sediment being deposit on top of them, and then they can begin to root. Mangrove roots can trap sediment and then slowly start building an island. As those roots are growing in and sediment starts to deposit, it can build and build and build. Instead of being distributed through wave erosion, that mangrove roots are stopping that wave erosion. And so we have building, and we can start to trap in that sand and make an island. Holy cow. Okay, super relieved that this is done. Remember, we're planning on an all vocab quiz a week from Friday and a test on chapter 6 a week from tomorrow. Yes, we were thinking about a test tomorrow, but it's not. It's going to be a week from tomorrow, so on the 10th. Y'all got this. See you tomorrow. 5th period. Get ready for that test. It'll be timed, and you will have some written answers. Love you guys. See you tomorrow.